Hello, everyone. Today we're doing section 3.1. 3.1 is titled Definition of Derivative. So in the last lesson, you learned how to find the slope of a tangent line. We gave you a definition of that using a limit. We took what's called a secant line between 2 points, got it closer and closer and closer and closer together, and it gave us the slope of the tangent line using a limit. Mathematicians over time found out that this was a pretty powerful tool. Actually, it didn't seem like much at the time, maybe, but it kept popping up in other places. So some of you already know this, I'm sure. So since it started popping up in lots of other places, they decided to give it a special name because of the connections between speed and velocity and things like that, like you probably know. So they actually introduced this term called a derivative. What I'm about to do for derivative, I'm sure you've seen this, is going to look exactly like slope of a tangent line because it is the same. So it turns out that the derivative is the slope of a tangent line is a specific case of dealing with this derivative. But they decided to give this the overriding name of derivative. So whenever you hear derivative, slope of tangent line, they're totally synonymous. They totally mean the same thing. So when I come here, to give you the definition of derivative, it's going to look an awful lot like what you saw for slope of a tangent line, right? Limit as h approaches 0 of f of x plus h minus f of x all over h. Little notation. I'm going to show you some more notation in a second. That's the main notation we use for derivative. It's the way you say that is f prime. I'm sure you probably know that. But we say that derivative. So I'm not going to go through the same lesson I went through the other day. It's the same proof. I could show you the slope of the tangent line. But that's the definition. There's an alternate definition of derivative, which is this. It's the same basic idea. It's still taking a limit as 2 points approach each other. They're just changing the variables on you, basically. So the alternate definition is limit as x approaches a of f of x minus f of a all over x minus a. So it's really the same thing. It's just notation for notation purposes. If you were to draw a little graph here, and you know how we found this tangent line, you could call, one point here, I think before we called this x and x plus h. Hence, as x gets closer to x plus h, which is h approaching 0, you could also call this a instead of x plus h, and now you have x getting closer to a. So it's the same thing, it's just notation. When you use this definition to find derivatives, sometimes one of the definitions is better than the other. I would probably argue that 99% of the time you can probably get away with that definition. We might make you practice a couple of them. The other definition, this one tends to work a little bit better if you're dealing with like square roots. That's pretty much the only case. But either one's going to work. If you're asked to find a derivative, it's going to give you the derivative. So tonight's homework, they're going to just say things like, find the derivative of. It's really exactly saying the same thing as find the slope of the tangent line. It might be add a number, which means you have to plug in a number for x at the end. It might not be, and then you just leave x in your answer. Okay. I mentioned notation. There's all kinds of notation for derivatives. Again, the most common one that we're going to use is this one right here. It's called f prime of x. But remember, y is f of x. We start with y equals f of x. So sometimes we just say y prime to simplify it a little bit. The second most common notation will be this one. The way you say that is the derivative of y with respect to x. Yes, you say dy dx. You'll hear me say that, but what that means is the derivative of y with respect to x. We'll talk more about the wording of that a little bit later on. Again, here it's just the f replacing the y, and then here's just another way to make it a little bit more longhand. We hardly ever use these at all. They just come in handy sometimes in theorems and things like that when you're trying to manipulate things. For the most part, f prime of x, y prime, or dy dx is what we're going to use. So what we're going to do is right now briefly touch on what a derivative looks like from the function, because we want to keep in mind that derivative means slope of tangent. If you can keep that connection in mind all the time, it's it's going to make your life a lot easier in the long run. So I'm going to give you a little picture here. I'm just going to draw this out here, 1, 2, and 3. And then I'm going to put a little thing that looks like this. So here's a little picture of a function, okay? So this is f. So what we're going to try to do is take this function and draw its derivative. Now, you probably already know some more things about derivative from last year. We're going to try to pretend for a second that you don't remember any of that. Hopefully that is pretending. I know you maybe forgot them anyway. So what we're going to do is just think about the idea that derivative means slope of tangent, right? So at any point, if I want to graph the derivative now, right, so this is the function, right? Remember that the derivative is the slope of the tangent. We're not going to use that equation right now. We'll do that in the homework to just generalize some problems. Right now, we just want to think about that derivative is slope of tangent. So let's find an easy slope. If I go right here at the point x equals 1, that tangent line has a slope of 0. So if I come over here and graph 1, 2, and 3, that this must have a point at 0. And then I can do the same thing at 3. Notice that there's a horizontal tangent at 3, which has a slope of 0. So remember that slope is derivative. So I come over here, it's going to have another 0 there. Now, those are the only 2 points I can find the exact slope of. However, I can kind of generalize. If you look at these slopes here, all the slopes before 1 are tilted this way, so they're positive, or this way, whichever it looks for you. All the slopes over here, the tangent slopes between 1 and 3 are negative, and then they're all positive over here. So what that means is we have positive slopes over here. And notice also, not as a big deal, that as you get closer and closer, I know it's hard to see this. Let me try this again. I'm just going to redraw that real quickly. Yeah. As you draw these tangent lines, like that one and then that one, they're starting to get smaller, right? So they go positive, then they go negative. There's some negative slopes between 2 and 3. Then there's some positive slopes after 3. So very, very rough picture of what the derivative will look like. It's very rough. All we're really looking for are zeros, slopes that are 0, and positive versus negative. I don't know the exact shape, but that's kind of the basic idea. Now we can do the same thing going the other direction. So now I'm going to, give me 1 second to draw a picture here. I'm going to draw, this is a little bit harder to come up with examples on this one. So I'm just going to draw a little piecewise graph here. Whoops, we'll call this 2, we'll call this -1 here. I know my scale's not very good, sorry about that. So again, now we're going to go the other direction. That's the derivative. So now we're going to graph the actual function itself. So notice, this is a little harder to do. So notice, change colors here. This is why this is specific. Notice that the slopes, remember that the derivative is the slopes of the original function. So all of those slopes right there are 2. So if I go to the point, that point's 1, sorry. If I go to the point 1, okay, everything from 1 to the right has to have a slope of 2. So basically what that means is I'm just going to have a line like that has a slope of 2. I could be more precise. I could go rise over run is 2. So I could go 1, 2, 1 or something like that. I wouldn't worry too much about that. The idea is it has to be a line because all of these tangent lines then, hard to draw tangent lines to a line, but all of those tangent lines are the same. They're all equal to 2. However, to the left, notice to the left, all of the slopes, remember derivative is slope of the original function, all of those have a slope of -1. So I'm going to come back over here to my picture, and I'm going to draw a slope -1. So it's got to be negative. It's not as steep as the other one, so hopefully looks okay. Not quite as steep as the other one. Okay. That's all there is to that one. I don't know if there's a point here or not. I know people get confused because they see open circle here, but those are the slopes. It just means there's no slope there. If you come over here to this picture, and I try to draw a slope at that point, I can't, because some people go, oh, say, there's the slope. Some people might say, no, there's the slope. Some people might say, no, there's the slope. So there's no one particular slope there. Hence, there just is no slope. There could be a point. These open circles are just saying there's no slope. So tonight you're going to have to find derivatives using the definition, which is exactly what you did for slope of the tangent, and then maybe draw a couple little pictures. I think that's it for section 3.1. Let me know if you need any help, and you'll see me next for 3.2.